Hi everyone, welcome to our second video from section 14.2 on the topic of continuity. We'll start with a definition. A function f of two variables is called continuous at a point AB if the limit as xy approaches AB of the function f of xy is equal to f of AB. So embedded in this definition are actually three things that must be checked. In order for a function to be continuous at AB, we must first make sure that the limit of the function exists at AB. Secondly, we must make sure that the function itself exists at AB. And thirdly, we must make sure that that value of the limit is equal to the value of the function. Now, as in two dimensions, limits of continuous functions are easy and can be found simply by evaluating. Let's look at some examples. Let's first compute the limit as xy approaches the point 2, 1 of the function x squared plus 2xy minus y to the fourth. Now this function is what we would call a polynomial function of x and y. And this function is actually continuous on the whole xy plane, right? There's nothing that should give us any pause about this function. We're never dividing, we don't have any roots, and we don't have any logs. So this function is perfectly continuous on the entire xy plane. So in order to compute the limit, we must simply evaluate. So everywhere we see an x, we'll replace it with the number 2. Everywhere we see a y, we'll replace it with the number 1. So we get 2 squared plus 2 times 1 minus 1 to the fourth, which simplifies to 7. All right, how about 6b? We want the limit again as xy approaches the point 2, 1, this time of the function 4 minus xy divided by x squared minus 3y squared. This is an example of what we would call a rational function of two variables. And because we're dividing, we've got to be a little bit careful with this function because we don't want to divide by 0. But we can quickly see that we're only dividing by 0 at the origin when x and y are both 0. So that would be this function's only discontinuity. Since our limit is approaching a different point, the point 2, 1, where our function is perfectly continuous, then again we can compute our limit simply by evaluating. So we replace x with 2 and y with 1. So we get 4 minus 2 times 1 divided by 2 squared minus 3 times 1 squared. This simplifies to 2 divided by 1, or simply 2. All right. Next example. Let's determine where the following functions are continuous. Now, this problem should feel very similar to when we're simply finding domains. So remember, we're not allowed to divide by 0. We're not allowed to take an even root of a negative number, and we can only take the log of a positive quantity. So in a 7a, where our function is the log of x squared plus y squared minus 4, since we have a natural log, we must make sure that whatever we're taking the log of is positive. In this case, we need x squared plus y squared minus 4 to be greater than 0. Or we can rearrange to say that we want x squared plus y squared to be greater than 4. Think about what we will sketch then for our region of continuity. So the x squared plus y squared equals 4 would be a circle centered at the origin of radius 2, and then we want to be exterior to that circle. So here is the region where this function is continuous. Outside the circle, x squared plus y squared equals 4. All right, how about in b? F of xy is the arctangent of x plus the square root of y. Now don't let the arctangent spook you. It's not on our list of things to be weary of, right? We're not dividing by anything. We don't have any logs. So the only thing we have to worry about is that square root. We need what's under the square root, the y, to be greater than or equal to 0. And that's it. So think about what we'll sketch. Think about the xy plane and where we'll shade in that y is greater than or equal to 0. Here it is. So here's the region where this function is continuous. One final example. Suppose f of xy is the following piecewise function. It's defined to be xy divided by x squared plus xy plus y squared for every point in the whole xy plane except for at the origin. And at the origin, our function is defined to be 0. All right, let's think in terms of continuity. Now, looking at this rational function, the rational function is perfectly continuous everywhere except when dividing by 0. So everywhere except possibly at the origin. So the only possible discontinuity of this function is at the origin when x and y are both 0. So in order to check for continuity at 0, 0, we're going to appeal to the definition. We must check whether the limit as xy approaches 0, 0 of our function is equal to the value of the function at 0, 0. And in this example, we're specifically told that f of 0, 0 is equal to 0. So we've got to check whether the limit as xy approaches 0, 0 of this function equals 0. Well, let's first see if we believe whether the limit even exists at the origin. So let's choose a couple of different approach regions and see what we learn. Suppose we approach 0, 0 along the x-axis, so when y equals 0. So looking at our function, if we replace all of the y's with 0, we're left with the limit as x approaches 0 of 0 over x squared. This is equal to the limit as x approaches 0 of 0, which is just 0. Okay. What if we instead approach 0, 0 along the line y equals x? So if in our function we replace every y with x, we have the limit as x approaches 0 of x squared divided by x squared plus x times x plus x squared. This cleans up to the limit as x approaches 0 of x squared over 3x squared, which is the limit as x approaches 0 of 1/3, which is 1/3. So we found one approach region, the x-axis, which gave us a limit of 0, and a second approach region, the line y equals x, which gave us a limit of 1/3. Since we've got two different paths leading to 0, 0, they give us two different values for the limit. That tells us that the limit of the function at 0, 0 does not exist. And since the limit does not exist at that point, then there's no hope of our function being continuous at that point. So we see that the function has a discontinuity at 0, 0. One final quick remark. Notice that the choice of paths, so we picked the x-axis just because it was easy. You could just as easily have approached along the y-axis. That would also have given you a limit of 0. And then our second approach path of y equals x, that one was chosen more strategically to make sure that every piece of the denominator would end up with an x squared so that we could combine those powers together. So that one was chosen a little bit more strategically. All right, so that's all for this video on continuity. I'll see you guys in class. Thanks. Bye.